All right. So in this last video for our introduction to rings section, we are going to prove a theorem. We're going to prove the following theorem. So it's a way of characterizing fields, one might say. So a commutative ring R is a field if and only if R cross, so the set of units, is just all the non-zero elements. So proof, well, if R is a field, then every non-zero element has a multiplicative inverse. Because that's one of our axioms for being a field. But this just tells us that the set of units, that is the guys with a multiplicative inverse, is the non-zero elements. Let me say 0 sub R just to indicate that it's just the 0 in R. And of course, if if the non-zero elements are for the reverse direction, if the non-zero elements are the, oops, gosh, I'm talking too fast here. If the guys with a multiplicative inverse are just the non-zero elements, well, then R additionally satisfies the multiplicative inverse property for being a field. Oops. So the difference between a ring and a field is two properties, every non-zero element having a multiplicative inverse and commutative. But our ring is commutative, so since R is commutative, it is a field. Because it has those two missing properties to promote ourselves from a ring to a field. As a quick example, we saw that Z mod M is a field if and only if M is a prime number. And we also saw that Z mod M cross is a collection of all A bars in Z mod M, such that if you were to take a representative of that A bar and look at the GCD of A and M, you get 1. And you saw in a homework that this is equal to Z mod M minus 0, so all non-zero elements, if and only if M is prime. Oops, prime. So this is a fact up here that we already knew, and this is us using the theorem, because this is certainly Z mod M is a commutative ring. And from what we did in the previous video, all non-zero elements are units in Z mod M when M is prime, and actually that's an if and only if. Great.